This is a exam 3 spring 2018, and they're asking that what is the electron configuration for zirconia Gr2 plus. So then what do you need to do? You need to look at the periodic table. Okay, so I'm going to look at the periodic table, and so turn it on the light. And the periodic table, where's the zinc? Zinc is right there, which is a number 30, right? Zinc is a number 30 with d orbital completely filled up, and that's what it is not zinc. Sorry, zirconia. Okay, I have to look at that. Zirconia is right there. Sorry about that. That's a zirconia. Zirconia is number 40 with 2 d orbitals and 2 s orbitals, right? So this is a number 40. And the zirconia itself is a, what is it? Closest a krypton, Kr. And then you have a 4s2, a 5s2. This is a 5s2. Okay, 5s2, 4d2. Okay, and then you need to get rid of 2 electrons, right? Your zirconia 2 plus. So which one do you remove? The one in the, when you come up to this, the energy level for this one is about the same, and then they like to get rid of the s orbital. Okay, so this is something that I think the nature of the d orbital has a lot more places to move the electrons around, and so that's they love to lose the one in the, actually one way to look at it is number 5 is an outer shell, so they want to remove that. They want to keep the electron in the d orbital as much they can. So that's essentially krypton is a 4d2. Okay, so that's the electron configuration. Okay, so number 17, what is the charge of the metal ion in the coordination complex? And this one is a fairly easy and straightforward, but but you have to know what you see. I think that I didn't talk to you about CO2 is a carbon monoxide. CO3 is a carbonate. And this is actually coming from the carbonic acid. If you remember one of the lab, we talked about the carbonic acid become the carbonate ion. So as you can imagine that this one is actually 2 minus. That's what they are making it. If you mix the H2O plus CO2, you make carbonic acid. And then when you lose 2 protons, and you make this carbonate ion. Okay, I guess this is only the piece of the puzzle that is you need to figure that out. So what that means is the overall charges on this is -2, and there are 3 of them, so you need to multiply by 3. That's a -6. So this side is -6 overall. Right? This, I don't know the charges, so let me just call it an X. And then overall, this is a -3, as the name suggested here. Right? So therefore, this one is +3. Okay? So if you know this nature of the carbonate ion, this is a very easy problem. And the answer is for this one is number 3, +3. Okay, so then you want to say cobalt with the 3, and that's what people write. Okay, the number 18 is which is a chelating ligand, and that's a question that which species is a functional chelating ligand, and chelate is some compound that has more than the 2 coordination more or than I don't know which is correct, more than 2 or more. 2 or more, I think that's a better way. 2 or more coordination ligand. That's a chelate. It's almost like, for example, this is we call the ethylene diamine, remember? And you remember the oxalate? and that's a 2 coordination. EDTA, that's a 4 coordination, and this is what I discussed in my the introduction of the crash course in the first part of the nomenclature. So that's a chelating agent. Okay, so I think I solved these 3 problems, and if you have allow me, I'd like to talk to you about very quickly about this because this is just related to what I just said here, and this remaining 3 problems, I will go to the reverse order. Which one can have a chiral isomers? I see a bunch of ins here, right? And the one way to remember is metal with ethylene diamine 2 with some kind of halogen complexes, or metal with ion with 3. And this case is when you have a 2 ethylene diamine with a 2 halide, and this must be a cis. These are the 2 examples where they can have a optical isomer, chiral isomers. They both have an octahedral structures. So you look for the answer now. Here, which one can have an optical isomer? I see the answer right there. Right? So this is same as this. So that's an octahedral. I don't see other answers that can be a choice of our answers. And if you look at here, this one is another example where this one is actually, they can have a cis or trans geometric isomers. And so does and then this one is actually, the answer for this is an A. And do you see this, which coordination compound form the linkage isomers? That's the one that I just talked about. You know, NO2 can have a nitrogen, can form the docking with a metal, or oxygen, NO. Is twisted. Thanks for staying with me, but I think I just wanted to give your time more productive here. So so this is where those lone pairs, which one is connecting to. So if you look at here, that's a nitroso, and this is a nitro that is a docking to the central atom of the ion. So that is showing as an example of the linkage isomers. If somebody asks you what are the other example could be the linkage isomer, I can give the same thing, like Fe, hexacarbonyl, and then SCN versus Fe, CO, pentacarbonyl, and NCS. If somebody write the things like that, that can be also the linkage isomer pairs as well. So that's an answer for the answer is C. And this one is pretty easy for you to know. The one it's a little difficult version of the nomenclature. This is in the anion side, right? So this is a platinum, but you ended up with a platinate, and this is a cobalt, but cobalt is a cobalt in the cation side. So this is a cation side, quote unquote. This is an anion side. Anion side, you're always having this different variation of the name. Oh, okay. I forgot to show the whole screen for the document. At any rate, I think that this is I'm going to repeat this one problem again in the extra session class for tomorrow evening. Okay, so let me stop here.